Welcome to a video on Class A amplifiers. Right, so we're going to have a look at the BJT and the MOSFET Class A amplifier. Um, Most importantly at voltage transfer characteristics, then some designing, and then we're going to look in general at the power dissipation and efficiency um, for these. And we will list the advantages and disadvantages, and lastly do some simulations. Right, now the purpose of a Class A amplifier, Class B, Class AB, is to do some sort of driving. It is a power amplifier. Okay, so that is the amplifier that you get at the end before you have output to, let's say, something like a loudspeaker, whatnot. So it is basically a common collector or a common drain kind of setup, and your aim is to drive small loads. Now, most of our amplifiers, even op amps, can't drive very small loads, and that is why we need power amplifiers. Right, so the voltage in must be equal to the voltage out, but with some oomph to drive a load of some sort. Okay, so for the Class A, the typical kind of output that you can get is at the top of the waveform. You will rarely have any issues unless you reach the top rail. So in my examples here, I'm going to use plus minus 10 volt rails. The issue comes in typically at the bottom, where it can start clipping early or a little bit later, or you can almost reach the rail. Now that's a part where the design of the Class A amplifier comes in. Right, so looking at some circuits first, if both of these are the same, sort of. If we look at the top half here first, this is a common collector kind of configuration. And what we have here at the bottom is a current source. Okay, my problems here I'm going to do using current sources that we have built. Since using a perfect current source in LT will not yield the correct results that you would expect. Okay, so first thing that you always want with these circuits is you want your transistors to match, um, especially so that the saturation currents of both of these um, transistors are exactly the same. Then the VBEs down here can match perfectly when designing a current source. Right, you can do the same using a diode, but it is sometimes tricky to match these because the saturation current of this um, diode needs to be the same of the transistor. Okay, their surface areas needs to be the same. So it can become a bit tricky, but you will see configurations like this with a diode included and some form of resistor. The best way, however, to do this is to use matched transistors. So I'm going to go with the example on the left in our calculations. Right, so how this amplifier works is on a positive half of input here, current will be supplied through our driving transistor right here. On the negative half, this transistor will kind of switch off and current will flow through the current source. This is technically a current sink. Okay, so positive will be supplied from the top, negative will be supplied from the bottom. Right, so the current of this current source is also the peak current that you want on this load resistor. So for 100 ohms and a 10 volt rail, that would be 100 milliampere, and you will have to design this current source to deliver 100 milliamperes as well. If it's less, you will start to see this clipping that we have here. Right, so it's a current source design. The current flowing on this side is the same as the current flowing on that side. So one of the defects of this design is typically that we have a lot of current sources and current everywhere that's not always in use. So it's not very efficient. Right. So the most important part of any power output stage is the voltage transfer characteristic. Right? And the first thing that you notice here, this thing is not going through 0, 0 in the middle. Note that there is no biasing on the input of this transistor right here, so it requires VBE to switch on. Okay, so this offset that you have here on the input and on the output is due to the switching on voltage of our transistor 1. Okay, so our offset is due to this transistor right here. So if you don't want offsets in the end, you need to remember to include some form of capacitor, or if you don't want to do some capacitance out here at your input signal, you need to supply some form of DC voltage just to lift it up. Right, so there is two options to solving that, or you can just leave it as it is if you don't mind the DC voltage. Right, so a voltage transfer characteristic. So for any input voltage, we have a given output voltage. We will saturate our amplifier near the rails. Now what you'll notice is we do not get right onto the rail like we should. But we should remember that transistors have saturation voltages, and this is typically at 0.3 volts. For saturation, deep saturation is at 0.2 volts. So you take the rail voltage. This is the top transistor, so it's dependent on the saturation voltage of the top transistor. And here at the bottom, VEE, which is a negative, so minus VEE plus the saturation of the bottom transistor will give us this clipping here at the bottom. Right. Now, as our current of our current source decreases, we will reduce the amount of output we can have on the negative cycle. Okay, so we need to design our current source to be just right. So typically, if Iref our load is the same as VEE plus our saturation voltage right here, we will be fine in the current source department for design. So this is the only design part that we have. So with our rails at 10 volts, our output maximum and minimum is when we subtract our saturation at 0.3, so that will be 9.7 and minus 9.7 volts. Our reference current, so the current we need to pick in here, would be our VEE plus our V saturation over our load resistor, and that will work out to 97 milliamperes, which is close to the 90, the 100 that we had originally. Most people will just ignore the saturation in any case and get 100. So there's nothing wrong with removing the saturation and just over designing this a little bit. In any case, assuming all our transistors switch on at the same point, for this 2N triple five zeros at 100 milliamperes, the VBE is at around 0.9 volts, not the normal 0.7. So always have a look at your data sheet to see if it switches on at a different point than 0.7. It might be important in certain cases. If you don't know, just go with 0.7. I'm sure it will be fine. But be aware that there is transistors that switches on at higher voltages or requires a higher base emitter voltage to operate at the correct current. Something like a Darlington pair transistor might switch on at 1.4 volts, which is kind of a lot when working out a reference resistor. Okay, so this RF here supplies into this transistor, and you'll note that the current must go into the transistor, the current goes down here into this transistor and into the transistor on that side. So they're matched. This is kind of fine, but we need to remember to account for IB2 in this calculation. If it's a high beta value transistor, you can neglect the effect of IB2, but if these have beta values of say 25, which can be typical for some power transistors to have low beta values, you must remember to take this small current that needs to go into this transistor into account. Right. So calculating the resistor on this side is basically applying Kirchhoff's. So first off, the VBE on this side and the VBE on that side will be the same. That's how the current is being mirrored. So if we assume this current flows through here and through this transistor and we ignore base currents, the collector current here is the same as the reference current flowing through the resistor. And we have our VEE minus our VBE voltage right here. So minus minus is our 0 over the reference current will give us our reference resistor. Right. So this works out at 93 ohms. And we always choose this resistor downwards. So 82 ohms would be the best. Okay, so I'll show this later in the simulation. Right. If you go with a similar value to what's on this side, you will probably have this case where it saturates at minus 9 volts and not 10 because you did not account for the VBE drop on this side. Okay, but these two resistors will be in a similar range. So 82 and 100, not that far off from one another. Right. The power dissipation of a BJT. This is VCE and we have IC flowing. That is power contributor number 1. Power contributor number 2 is our VBE and the base current flowing. Now typically VCE IC is much greater than whatever we have down here. So the power of a transistor is approximated to be VCE IC of a transistor. Okay, calculating the power dissipation over a power transistor is very important, especially when you need to choose one, so that you don't burn out the transistor or overload it and poof, gone output stage. Some of these transistors can be quite expensive. Okay, so always do the power calculation of your components. Right. The maximum over this transistor is VCC minus VEE, so the whole rail can be over this transistor when it's fully on. So it's 2 times VCC. There is constantly amount of current of I reference flowing through this transistor, sometimes 2 times the amount of reference current. So the maximum in IC is 2 times Iref, but they do not peak at the same time. So for this transistor, it averages out on just VCC Iref for the dissipation. Okay, as a side note, the power dissipation for a MOS transistor is just the drain source times the drain current, since there is no gate current flowing. In certain cases, there might be a leakage current into the gate, but that is microamperes on hundreds of milliamperes. So it still doesn't really matter. It will still be the same kind of approximation. Right. The efficiency of a Class A amplifier. So we need to find the load power and the source power, and the ratio that will give us our efficiency. So on the load, if we're on a peak voltage, we must divide that by the root of 2 to get a RMS value. So that will be, the load power would be half times V out peak squared over R load. The maximum supply power is 2 times IRF VCC, because we have this extra current source here on the side. And at maximum efficiency, our peak output will be the same as our VCC. This is when we're neglecting the saturation voltages, would be the same as Irev or load. Okay, so peak, source, and load voltage will be the same at maximum efficiency. Okay, so if we break this up, that will cancel, and I missed a half somewhere. Oh, there. And this will be a quarter of the efficiency. Fixed. Sorry about that. I forgot this to include it in here. So the efficiency of this will be 25%. 10 to 20% for real applications, since there will be more losses than what we included in here. So 25% is bad. Only 25% of energy reaches the load. The rest is all dissipated in these components right here. So Class A amplifier is kind of good. Not much offset, easy to design, whatever, but there is huge losses in it. Right, for MOSFET we can use a similar kind of setup. Just instead of having VBE everywhere, we will have our VGS voltages. So we need to calculate a VGS if we want to do the current source calculation. We will have a larger offset due to our VGS, but if you pick the right MOSFET, you can have a smaller offset than our BJT. As a side note, if threshold voltage is much lower, you can get away with a smaller offset voltage. Any case, but since a MOSFET is voltage biased, instead of using a current source or a current mirror, you can use a voltage divider or some other form of reference voltage here at the back, which draws less current. You can get a little bit more efficiency out of your Class A MOSFET amplifier. A voltage transfer characteristic, um, bigger offset due to our VGS on this one. Same approach for our load and reference current, which will set our minimum output here. But there is a bit of a change in our rails or our maximum outputs. So here we have VDD minus IREV RDS on. Now this RDS on is every MOSFET when it's completely on has a very small resistance through it right here, typically in the milliohm range. Okay, so a couple of milliohms times a milliampere current kind of deal right here. This is a very small number. This one as well. So we can get very close to the rails when using MOSFETs. Okay, so it's not 0.3 anymore, it is a couple of millivolts now. Right, so that's one of the advantages when using MOSFETs, but the big disadvantage is this huge offset right here, but you can decrease this quite a lot if you pick the right MOSFET. Right, designing wise, for the transistor that I used, our transconductance is 27 amperes per volt squared, our threshold is 2.4 volts, and our RDS on is 12.4 milliohms. Right, so this being milliohms times 100 milliamperes, we can neglect this effect in general, so the output maximum and minimum is approximately plus minus 10 volts, so we can achieve rails here. Okay, so IREV must be larger than VSS over R load, IREV being 100 milliamperes. All three our VGSs will be the same. Calculating the VGS voltage required, 2.486 volts. This is the offset that we have, but this is also the value we need to use to calculate our reference voltage, or our reference resistor rather, sorry. So the current flowing like this, we have our VSS and our VGS value, and that will determine our resistor. So minus VSS minus VGS3 over our reference is 75.14 ohms. We pick that downwards to 68 ohms, and our design is complete. Right, so a quick look at the advantages and disadvantages. We haven't seen any distortion on our outputs, and I'm not talking about the clipping right here if you design your reference current wrong. The design is kind of simple. The disadvantages is that we have 25% efficiency and we have offsets. Okay, there is ways to deal with the offsets. But yeah, so let's go and have a look at our simulations. Right, so our first simulation here I have set up with a 9-volt peak input signal, and our reference resistor ranges from the 82 that we designed for, then the 100, which is the same as the load, and a 120 ohm, just to make a point. So if we do a transient, here is our input signals, and there is our output. Now you'll see that it doesn't clip at the top, but it does start clipping at the bottom as we're approaching our um, rail right here. So the blue one is our 82 ohms. That's our 100. So we would have picked the same resistor both sides. It would have clipped, and that is just the 120 ohm to make a point. Any larger resistor here, this amplifier will work fine. All three are laying on top of one another right here. Okay, so the lowest impedance is the one that you design for. Okay, you don't design for the highest impedance right here, you design for the lowest. Right, so 9 here, because if we make this 10, which would be our rail to rail operation, it will start to clip because we're going to hit the bottom rail. Right here. Okay, so there's our bottom rail, but we are not getting close to our top. So if we insert the offset of 0.7 volts, it is not entirely fixed. It clips at the top, it clips at the bottom, because we did not consider the drops that we have. So if we make this 9.3, it will be fine. If we make this 9.7, it is also fine. So that is right on the edge there. Okay, so this is on that edge of saturation, and here as well. So we could fix the output offset by applying a bit of input offset. So this transistor is switched on, then we can almost reach our rails, but we can't due to the saturation. But there is our minimum and maximum output proved. Just add some offset right there. Right. The DC was shown in details in the presentation. So here we go. Including the offset here in the signal will not take it away in this voltage transfer curve right here. But I'm sure if you include some form of a bias here to automatically remove or add the 0.7 on this side, it will be included on here. It will be fine. Just remember, if I were to remove a DC using a capacitor right there, note that this changed to femtovolts. You need to measure on this side. If you want to do the DC analysis, you can't measure on that side of the capacitor anymore, because capacitors are DC blocking. So when doing a DC sweep like this, remember to perhaps remove some capacitors if you want to see the effect over to a load resistor or something. Also note that due to the capacitor, all this loading effects um, of a different reference resistors disappeared on the low side here. Okay, so having this cap here makes this very inaccurate. Okay, so transient running, see that is still there. It didn't disappear due to what we did. And let's remove this DC quickly and let's make this 9 again. So there's our input, there's our output, and see the DC on our output of that 0.7 has been removed due to this capacitor. Okay, but I think it would be best to do the DC removal here on the input side of a DC nulling of sort. Any case, that is the BJT simulation. Let's go to a MOS one. Right, here is our MOS amplifier. So let's run this transient. See that I used a 39, a 68, and 100 ohm, where the 68 was a calculated one, and they are almost lying on top of one another. We are practically going to the rail right here. So if we do some offset removal, let's say we add 2.5 volts here and make this 10 volts, we have pretty much a rail to rail operation for this amplifier. Okay, so you can go quite far with a MOSFET Class A amplifier and be more efficient if you do a voltage divider or some other form of reference right here. And having the offset added automatically here at the input side would be quite easy with the MOSFETs. Just have some huge resistors there and you can sort it quite easily. Any case, let's have a look at the DC characteristic. And here again you can see that big offset due to the fact that you're using a MOS, but it can be fixed. So not much to show here. The only decent thing to show is this rail to rail operation almost, and the fact that we have a huge offset on the input and output. Okay, there is not much to say further about Class A amplifiers. They are easy to design. They are easy to get operational, considered to some other amplifiers, but they are very inefficient. So this is a typical op-amp output stage would be a Class A amplifier. If you go and look at many schematics of operational amplifiers, you'll find some form of a Class A at the output. But that is for milliamp outputs only, so not huge driving circuits for 100 ohm resistors or speakers or whatnot, and that's why op-amp can't drive a loudspeaker, and you need to apply some form of stage like this. Any case, thank you for watching and see you in a next video.